Now, with energy levels, as I mentioned in the last video, it's not so much about the energy levels themselves, it's about energy level transitions. So when an electron does jump to a higher level, and again, using that word jump, not quite the best word, but we'll stick with it. So when an electron jumps to a higher energy level, it needs a specific amount of energy. We can't just cause it to jump up if it doesn't have the required amount of energy. So they must actually absorb, or the atom itself must absorb exactly the right amount. And that right amount is the same amount of energy as the transition that we're dealing with. So same amount of energy as the difference between the energy levels. So easiest way to talk about that, or to have a look at that, is to do an example. And so if we consider hydrogen, so going from n equals 1 to n equals 3, so we'll skip 2 and we'll have a look at what happens to 3. And again, sticking with hydrogen, given that it's the simplest, the difference in energy between those two levels will be the energy for the third level minus the energy for the first. And referring back to the energy level diagram, E3 is negative 1.51. We're going to subtract from that E1, which is negative 13.58. And that gives us a value of 12.07 electron volts. So that means to jump from n equals 1 to n equals 3 needs to have exactly 12.07 electron volts. A little bit more than that, or a little bit less than that, and the electron will remain in the ground state. That's because it can't transition to slightly above the energy level or slightly below. It has to have exactly the right amount. Now, that energy can be absorbed from a few different sources. So the first one that is probably the most obvious, it can occur from collisions with other particles. So we could even, by other particles, we literally mean anything. That so bombarding an atom with a beam of electrons or alpha particles, whatever it might be, if they have the right amount of energy, then they can cause that atom to be energized. The other one that we're going to focus on a little bit more in detail, though, are photons of light. Now, a photon of light can be considered just basically to be a packet of energy. So if a photon has the right amount of energy, then it's going to cause that atom to be energized to the higher energy level. Now, an electron in a higher energy level is basically going to stay there only for a very brief period of time. So the same way that if you throw something up into the air, it doesn't sort of hang around at its highest point for very long. It reaches its highest point and then falls straight back down again. So similar sort of thing here. Electrons in those higher energy levels are going to quickly fall, and again, not the best word to use, but it's probably the easiest to wrap our minds around. It's going to fall back to the ground state. And when it falls back to the ground state, it is going to re-release that energy. So the energy it's absorbed, it's going to release that energy. So releasing energy in the form of a photon of light. Now, when I say photon of light here, I don't necessarily mean literally visible light. It could be infrared, ultraviolet, or anywhere else on the electromagnetic spectrum, but basically just looking at it being a photon. So if we go back to that example again, we had going from n equals 1 to n equals 3. If we then have from n equals 3 to n equals 1, that transition or that difference in energy is going to still be the same. So whatever it gained going up, it's going to lose that much as it falls back down. So that was 12.07 electron volts. And so that means that a photon with 12.7 electron volts will be produced. Now, that was for the transition from n equals 3 to n equals 1, but that's not the only possible path that can occur. So when falling from higher energy levels to lower, there could be any number of possible transitions, and that's assuming that there are some intermediate levels that it could fall through. So when falling from higher to lower energy levels, the electron may transition through other energy levels. And as it does so, that means that there are going to be other photons emitted as well. Now we'll stick with this simple example of n equals 3 to n equals 1. And that means that there can only really be one other energy level that can fall through, and that means then that we could have it falling from n equals 3 to n equals 2 and then to n equals 1. So in the first instance, falling straight from n equals 3 to n equals 1, now it's going from 3 to 2 and 2 to 1. Now when it falls from n equals 3 to n equals 2, that's going to emit a photon of 1.88 electron volts. You can go back and check that if you want to, looking at the energy level transitions. And then from n equals 2 to n equals 1, we're going to see another photon of 10.19 electron volts. Now if you add those two together, you'll notice that they give us that same value as 12.07. So the energy that's lost as the electron energy that's radiated as photons, as it falls from n equals 3 to 2 to 1, the total amount is the same as the transition from n equals 3 to n equals 1. Now if we were at n equals 4, there are a number of different transitions there. It could go from 4 to 3 to 1, 4 to 3 to 2 to 1, 4 to 2 to 1, or just straight from 4 to 1. So a number of different combinations, and in each case a photon of light will be emitted corresponding to that energy level transition. We'll have a look at a few more calculations like that in class.